Hello and welcome to the Design and Analysis of Reconfigurable Systems group project. Let's go over the presentation, and yeah. So this is the high-level overview of how the HPS is connected to the AES core. The AES was actually created through Cyber Workbench. So the AES is connected to the HPS through an Axe4-like slave, and the Axe4-like slave has 64 configuration registers, which are written to and read by the HPS through the HPS to FPGA lightweight Axe master bus. So the HPS writes the plaintext and key to the registers. The AES core writes the cipher back to the registers, which is then read by the HPS through this Axe4-like bus. This bus width is 32 bits. Let's go over these configuration registers. So there are 14 configuration registers for the key, plaintext, cipher, and the control of the AES core. So the registers 0 to 3 are used for the plaintext, 4 to 7 for the key, and 32 to 35 for the ciphertext. Register 8 is used as a toggle, which signals to the Aes Accelerator to begin encryption. Register 36 is used as the finish signal, which signals to the HPS that the AES core has finished encryption and that the result can now be read. Let's now go over the algorithm. So first of all, the HPS writes the key and the plaintext to the configuration registers through the Axe interface. HPS then sets the toggle to 1, which waits for the AES core which basically signals to the AES core to start encryption, and it then starts waiting for the AES core to set the finished bit. This is all done through the Axe interface, and these bits are essentially registers in the config regs, as stated previously. So once the toggle bit is set to 1, the AES core reads the key and plaintext from the configuration registers. It performs encryption, writes the cipher back to the configuration registers, and then it sets the finished bit to 1. So the HPS, which was waiting for the finished bit to be set, now that it's been set, it reads the cipher from the config regs and then clears the toggle bit. The clearing of the toggle bit basically brings the AES core back to the wait for toggle state, so where it is waiting for a new key in plaintext, basically. So the HPS then verifies the result using the software Gorgon reference. If verification is successful, the HPS then decrypts the cipher and prints the decrypted output. Let's go over the design decisions. So the main design decisions were in the pragmas to set in the AES. So here we set all loops to unroll and the arrays to be synthesized as registers to get the lowest latency possible to get the highest performance. This is typical in the FPGA case. We did not consider pipelining because we're doing one at a time. If we're batching it, then pipelining will improve throughput. So the latency index reported by Cyber Workbench for the final AES core was 9. So for the Axe4-like slave interface, we used the fully pipelined implementation, which gives maximum throughput. So one thing that one problem that we came across was when actually setting the synthesis frequency of 50 megahertz in Cyber Workbench, this actually fails timing in quarters. So we had to actually raise the frequency in Cyber Workbench when calling BDL to get timing to pass in quarters. So this essentially just alters the architecture to give more slack, basically. All right, let's go over the utilization. So total utilization in ALMs was around 39% of the available ALMs, with 7,471 registers, 382 pings, 526,336 block memory bits, and 0 DSP blocks. Now let's go over the speed up. So to test the speed up, we actually took an average of 100 encryptions and tying both the software and the FPGA implementation. In this case, actually, we randomized both the key and the plaintext because we want to get rid of any input dependencies. So the AES code took 6.53 microseconds, while the software took 139.1 microseconds on average for encryption, which is a 21 times speed up Alright, now let's go over the architecture. First, let's look at the Quarkus code. So, this is the top module, and this is just basically the standard top module you find in the my first HPS if FPGA code. The yeah, this is just that top module. Let's go ahead and look at the platform designer. So the difference here is we've added our AES accelerator. So demo axis is basically our axis for like slave, and inside that our accelerator is there. So we've connected the slave axis for like slave to this HQF lightweight axis masker. Okay, now let's go over the demo axis code. So slave mem is basically the config registers. We've just instantiated the AES core here, and then we've written the AES outputs to these locations. So 32 to 35 is the cipher, and 36 is the finished bit, as we see here. And this is the AES core, which is just generated through HLS Cyber Workbench. Let's go over now the code. So the code, yeah, this is just some declarations, and this is the reading of the input, scripting new line, and then we fill that input into this variable. Here we get a random key, then we print that random key. This is the mapping of the AXI4 registers into virtual memory, and now here we start into the main part of the acceleration. So we write the key and plain text to the configuration registers. So it's basically on here. So these offsets are defined in this header file here. Just write the plain text and the key, and then we set the toggle to 1. Then we wait for the FPGA to finish. So while the finish is 0, so once the finish is 1, the FPGA is done. Then once it's done, we read the output and we clear the toggle. Then we print the cipher, perform software encryption through the Gorgon reference, and then we compare the two. If they match, as compare matched, we print ciphers matched. Then we perform decryption again through software, and we print the decrypted output. That is the software. There's also a second part here. This is essentially how the performance testing code, which we use to test the performance. We run this randomized 100 times randomized for key and plain text. So there's an if-def that you can set here to compile for the performance task. All right, now let's go through the implementation. So as you can see, I've run it once already, but yeah, let's go over that again. Let's just program the FPGA. Now let's run our code. So let's type in, let's say, test or something like that. Okay, there we are. So we have a random AES key printed, and we have the cipher from the accelerator, cipher from the software. Ciphers match means these are equal, and we have the decrypted plain text from the decryption. So that's pretty much it for this project. Thank you.